Alright, hello everybody. Sorry for the background noise, I gotta record this during normal office time here. So, we're moving on from our quadratic time sorting to stuff that is better than quadratic time, or at least we hope it will be better than quadratic time. And the question we want to start with is, like, how do you know that's even possible, right? Like, of course, you know it's possible. You can look it up in a book or whatever, right? But that wasn't always the case. There was a time when, like, sub-quadratic sorting algorithms just hadn't been discovered yet. So, like, every algorithm was, like, discovered or invented by somebody. And before that, like, it didn't exist. So that means that, like, there was a point in time at which the sort of whole field of computer science did not know whether it was possible to do sorting faster than O of n squared there. Like, we didn't have those algorithms yet there. So the interesting thing is we can demonstrate, we can construct a proof that it is possible to sort in better than O of n squared time. So even if we don't have an algorithm to do it, we should know that, like, oh, that algorithm is actually possible. So I'm going to kind of walk through like a sketch of that proof in this one here, and then after that, in another video, we'll move on with the actual algorithms here. Okay, so the idea is we want to show that it's possible to sort in n log n many comparisons. We're assuming that our sort of only tool we have available to us is comparing elements of our sequence here, so that that kind of gives us the most general sorting algorithm here. So we'll start with just like 3 elements here and consider, like, what comparisons would we need to do to sort this sequence here. We're only worrying about the comparisons. Like, you could always do like some swaps at the end to like put everything in the right order. So basically we're just figuring out like what the permutation should be and not actually like, permuting it there. I'm also going to assume that there's no duplicates, right? All the elements are distinct, because duplicates actually make it easier, right? If we have duplicates, then it doesn't matter what order you put them in there. So those are my assumptions. So we know that we have 3 elements and they're all distinct elements, but we don't know what order they're supposed to go in. So what we're going to do is we're going to build a decision tree showing all the sort of sequences of comparisons that we might need to do to sort these 3 elements here. So each of these like comparisons here that I'm going to write in like a box like this, something less than something, that's a decision, right? And since we're assuming that the elements are all distinct, that means that this is either going to be true, meaning that it's less than, or false, meaning that it's greater than. There's no equality possible, right? So if we do a bunch of these comparisons, we can figure out what order things should go in. So for example, like, let's say we start at the top here and we compare x and y, right? If that is true, then we can do another comparison and compare y and z. And if that one is true, then we know what order stuff should go in. It should go in the order x, y, and z. So we'll write that answer in like green and like angle brackets to be like, okay, we figured out one of the sort of possible answers here. So we'll start with just like, you can compare any of the 2 elements here, but we'll just compare the first 2 there, x and y, right? So that can go true or false, right? True means that over here, x is less than y, and over here, that means that y is less than x. If we go to the left, right, again, we can do another comparison over here, and then that can go one of 2 ways here. So if we know that x is less than y, if that one comes up as true, and if we know that y is less than z, that one comes up with true, then down here, we can give an actual answer, right? We can say, okay, x is less than y is less than z, and thanks to the like sort of transitive property of less than, right, we don't have to ask if x is less than z. We just kind of get that information for free. So we have one of our possible answers down here. If we go down here, though, right, if we know that x is less than y, but this one is false, that means over here we know that z is less than y. We don't yet have enough information. We know that y is going to come last, right? We know that y is greater than x and y is greater than z, but we don't know the relative order of x and z, so we have to compare them as well there. Depending on how that goes, we either get xzy or zxy. Y is in last place in both of those. If we go over here on the right-hand side here, right, things are just sort of symmetrical. So if I know that y is less than x, and I know that z is less than y, then I kind of get for free the fact that z is less than x. That's thanks to the transitive property, so I know what my answer is over there. And if I go in the sort of interior here, again, I get kind of like the mirror images of what I had over there like that. So this is a complete decision tree for a sequence of length 3. So any sequence of length 3, you can follow the decision tree and it will tell you how to sort those elements there like that. Okay, so the thing that we are interested in here, the runtime of this is the number of comparisons, and that is the height of the decision tree here. Like, how long does it take me to get from up here at the top of the tree all the way down to the sort of bottom part of the tree there. So we'll call that H. So for this tree here, H is 3, but that's only if n equals 3, right? We're looking at specifically n equals 3 here like that. So what we want is a relationship between n and h, so that we can say that, like, for any particular n, how tall will the decision tree be? And then that height, that becomes our runtime. So our runtime is O of h, but we want it in terms of n. Okay, so we'll kind of do this a little bit of a roundabout way here. So we're going to start by looking at the width of the tree, like the number of answers along the bottom of the decision tree. So in this case, the width is 6, like that right there, right? So the width is pretty easy to determine from n here. It's basically just the number of permutations, n factorial there. And that's because, like, you know, if we're trying to figure out, like, what are all the permutations, like, there's 3 choices for the first spot, and then only 2 choices for the second spot, and only 1 choice for the last spot, you multiply those up and you get 6 there, like that. As n gets bigger, the width of the tree is not exactly n factorial. Sometimes for larger n's, some permutations occur more than once as solutions here, but it's always within a constant multiple. So we can say that the width is, like, you know, approximately n factorial there. Okay, so now we want to connect h with n sort of like via the width that we just calculated there like that. Because our decision tree is a binary tree, every sort of like comparison, right, is true or false. We're assuming that there's no equality, so everything that comes up is either true or false there. Each decision has at most 2 children below it there. Because each node in the tree, each comparison can have at most 2 children, the width of each layer is at most double that of the width above it there. So like layer 0 at the top of the tree, of course that only has 1 thing in it there, but then the layer below that can have 2, and then the layer below that can have at most 4, and then the layer below that can have at most 8, and so forth like that. So they grow as like powers of 2, right? 8 is just 2 cubed, like that right there. So if we have a height of h, the maximum width along the bottom layer is going to be 2 to the h there, like that. All right, so we're almost there. We can put the pieces together. So we know that our width is approximately 2 to the h, or if we sort of like, you know, throw a log on both sides, we know that our height is going to be log of the width of the tree there, like that. We know that our width is in the ballpark of n factorial, so then we can substitute this w in over there, and we get that the height of the tree is big O of log of n factorial. That's probably not a logarithm you've seen, right? Like how does that relate to like our sort of other runtimes? Is that like better than n squared or n cubed or log of n? Like how does that kind of relate to stuff here? So we'll do a little bit of algebraic massage on log of n factorial to turn it into something that is a little bit more friendly. So n factorial, right, is n times n minus 1 times n minus 2 times blah, 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 times 2 times 1 there. What if we look at n to the n? So n to the n is just n times n times n times n. It has as many terms in it as n factorial, but they're all n's. Like they don't sort of change there like that. So it should be pretty obvious that n factorial is going to be less than or equal to n to the n here. Since n is like a size, right, we don't have to worry about like negative exponents or anything like that. N is always going to be greater than or equal to 0, and we won't worry about like what happens when this is like 0 to the 0 there, like that. So since, if you remember the definition of big O, right, big O has a less than or equal to sort of built into it there, that means we can say that n factorial is big O of n to the nth power. This actually goes both ways. Proving it the other way is a little bit more gnarly, but you can also say that n to the n is big O of n factorial. So it's sort of like both directions there like that. So this gives us what we need, because now we can go back to the thing that we originally had here and replace the n factorial with n to the n, giving us this, right? The height of our tree is big O of log of n to the n, and then if you have a power inside of a logarithm, what do? You pull it out to the inside, out to the outside, excuse me, and we're given this here. So the height of our tree is n times the log of n. Remember that we usually leave the base off of the logarithm when it's inside of a big O, because it sort of doesn't matter in that context there. So that tells us that, like, if we're using comparison-based sorting, we can do that. The sort of height of that tree is going to be n times the log of n, some constant times that, right? Like that right there. So that's the worst case. Like, sometimes the height is not that, right? If we go down the edges, then the tree is sort of shallower, but at the deepest point of the tree, that is going to be the height there, like that. So if you sort of put yourself back in the place of a computer scientist in 1930 or something like that, yes, there were computer scientists working in 1930, you know that there is a linearithmic, an n log n sorting algorithm, even if nobody has discovered it yet there. So, like, you know that it's something that's possible, even if it hasn't been sort of discovered yet there. Which is, like, I don't know, I think that's kind of interesting, the idea that you can prove that there's something there even though we don't know what it sort of is there. So anyway, now we're going to move on and look at the actual, like, sub n squared sorting algorithms, starting with merge sort. So that's it for this one. You can pop into the merge sort video if you want.